This section is 9.3, and we're going to discuss the concept of the moment of inertia. The moment of inertia is symbolized by the symbol I, and it is the rotational counterpart to the concept of mass. You recall that mass is the resistance to motion for translational motion. When we put a force on an object that has a mass m, this gives us the acceleration. That's how we're going to find that we define a similar concept of mass associated with angular motion. We're going to define moment of inertia capital I as the sum over I of all the masses times the square of the distance of that mass from the center. Units are going to be kilograms times meter squared. Let's just quickly figure out how we would define a center of mass for some simple problem. Let's imagine that we have a rotational center here and a massless arm here and a distance 4 meters out. We have a mass of 6 kilograms. And a distance of 10 meters out, we have a mass of 7 kilograms. Then how do we compute this? Well, the moment of inertia of this system right here, about this axis, remember it always has to be computed about an axis, is going to be the first mass times the square of the radius plus the second mass times the square of the radius. So it would be m1 r1 squared plus m2 r2 squared. The m1 is going to be 6 times 4 squared plus the second mass, 7, times the square of that radius, which is 10, times 10 squared. So this would be 4 times 4 is 16 times 6. Or 96. This would be 100 times 7 plus 700. So our moment of inertia I for this particular system would be 796. And the units there would be kilogram meter squared. I should put the box around the original equation because this is the important thing here. And that's just one example of how we would compute that. Well, let's see where this comes from. You remember that back when we looked at force and acceleration, we had force was mass times acceleration. So mass was the critical constant that multiplied our acceleration to give us our force. It told us how effective a force was in accelerating an object. It is the resistance to acceleration. If the mass is twice as great, the same force only gives half as much acceleration because of proportionality. Well, we're going to go back and look at the same kind of concept as it comes from torque. You recall that torque is R cross F. And we know that F, the F here we're going to use is the F normal. So we're just going to get R times F normal, or let's say F perpendicular. That way we can just eliminate the angle and look only at the force that's perpendicular to the radius. This is going to be R times, if we have a mass out here, it would be the force right here is the mass times the acceleration. But we recall that their acceleration is R times alpha. So this is R times m times the acceleration, which is R times alpha. And now this becomes such that the torque is equal to m times R squared times alpha. Therefore, you can see that just from that one mass that we get the important equation that this must be the concept that we want to replace our concept of mass, because the torque is going to have this proportionality with respect to the angular acceleration alpha. So we can now say that torque is equal to I alpha. And I is given by this equation, m times r squared. If we have many particles, then we're just going to add this up for each one to get our total angular acceleration due to a given torque. If we have that ensemble, I've written this out as torque is equal to all of these sum up because I've got one angular acceleration for the entire system. If we have something that's turning, there's only one alpha that we have. So the alpha is going to factor out every time I have different masses at different distances. They're always going to have the same alpha. Therefore, that alpha factors out and gives us that expression. Now, if we have a simple mass like we did here we had two masses, it's easy to compute what the moment of inertia is. But what do we do if we have solid things like a sphere? Well, if we have objects like that, like let's say a sphere, then you can see that for that sphere, the mass is distributed in a very complicated way. In fact, it's not even like a cylinder. It's much more complicated. And so we have to take each piece of matter and look at how far it is from the axes, take the square of that distance times the mass there, and do a triple integral over the whole mass. Well, this is pretty complicated. At this level of the course, we don't expect someone to be able to compute that, but we give them to you so that you know what the result is. And it turns out that for a solid sphere, the moment of inertia is 2/5 times the mass times the radius of the sphere squared. If it's a hollow sphere, it's 2/3 mr squared. If it's a solid cylinder, about the axis that goes through the center, it's 1/2 mr squared. So for example, let me just draw that one. You have a cylinder, got an axis that goes through like this, and we're going to ask how, if we take all of the mass times the distance out, times the square of that distance out, times the mass at that point, and do an integral over the whole cylinder, what do we get? The answer is, for a solid cylinder, the moment of inertia is equal to 1/2 mr squared. If we have a rod with the axis perpendicular to the center, there's a rod, like let's say a pole of some type, and we put our axis here, then in fact we find that the moment of inertia is 1/12 ml squared, where L is the length. But if it's on the end, then it turns out to be 1/3 ml squared. In other words, if we take a pole, make the axis here, and put the rod in this direction, we get a moment of inertia which is 1/3 ml squared. Now we might look at a problem of how we roll different things down the hill, but I'm going to solve that in a later section when we look at problems with dynamical motion that's with rotation.